Thanks very much. I think you've already given me enough of an introduction, and I don't like talking about myself very much. It's not why people are here, I don't think. So let's just jump straight into it. The reason I think we're all looking at this presentation is much the same reason that I think my book did unexpectedly well, which is that the book was written by completely ignoring all the other books on the subject, and I just went to the archives and read the files, and that's what you get. And the more I read in the files, I found more and more bits about Beatrice, and as per usual, you found that the story that you thought you knew isn't really the one that that we're all familiar with. So just to recap, she's essentially very famous for introducing a quick fix to the carburettors of the Spitfire and Hurricane aircraft early in World War II, essentially because the German fuel-injected engines could engage in manoeuvres which prevented us from following them. So that's what she's actually famous for. And it's remarkably difficult to find out anything else that she did. And that's a bit depressing, because actually the thing that she's most famous for is actually one of the smallest and least significant things that she did, which is not to denigrate it, but it's just to say that there's an awful lot of other things that we ought to know about her and we don't. And I also have a feeling that Beatrice would be, I think she'd actually be a little bit grumpy if she was best known for developing the restrictor, and I think you'll begin to understand why as we progress through the presentation. So if you have a look at pictures of Spitfires, very difficult to find one where they're diving in any other form than the one you see in front of you. In other words, to dive in an early Spitfire, you have to execute a half roll. And the reason for that is that the carburettor doesn't work, because it's a float carburettor, which is a hopeless device which has no place in an aeroplane. But there's a long story behind that. So there's another photograph, and it's another Spitfire, and it's diving or about to dive. And as you can well appreciate, if you've got a Messerschmitt in front of you and he can dive by just shoving the control stick forward and going into negative G, if you're going at 300 or 400 miles an hour, if you have to execute a half roll before you can follow him, he's probably so far ahead of you by the time that you've done that he's escaped. So what that essentially means is that many German pilots got home who would otherwise have been shot down, and that means that the next day that same German pilot would be back over the channel shooting down Spitfires who should never have been there. So it was a really big problem, and there's no place for jingoism in this presentation. So I'll say that I really think the seriousness of this problem has been quite severely suppressed over the years by the British, because it's very embarrassing, and it gets pretty bad, as we'll see. And let's see what happens. So this is just a letter from Ernest Hives. So this is February 1941. So this is after the Battle of Britain. So he's just saying here, this engine defect has saved the lives of many enemy pilots. And he's just talking about this modification. If we can get this into our squadrons, we're going to spring a nasty surprise. Now, this modification is the one that Beatrice Shilling came up with to fix the float carburettor. So it's interesting to note, first of all, that this was not applied in the Battle of Britain. So you'll find this talked about all across the internet, and very often it's said that this happened in the Battle of Britain. In fact, the fix did not occur in the Battle of Britain. That's when we were learning about it. This was later fixed, but it took an awfully long time, and even halfway through World War II it was still happening. So this is a Spitfire Mark 9. So this would be late 1942, and as you can see from the letter underneath, the Spitfire Mark 9 is still affected by, quote, this serious drawback. And if you look at the last sentence here, is saying this defect is so bad, if you ask a fighter pilot, it's literally the first thing they're going to complain about in the list of all the things they've got to talk about. So even in the middle of World War II, this was the thing that RAF pilots complained about more than anything else in terms of their fighting ability. And this was over a year and a half after Beatrice had introduced her restrictor. And the reason for that is it was only a partial cure, and that is that's no reflection on her abilities. It's a reflection on how awful a float carburettor is. So if we look at a float carburettor, it's really a glorified toilet system. That's literally what we've got. On the right here is the float bowl, and just like your toilet at home, there is a little valve that stops the water coming in once it's got to a certain height, because you don't want it to fall all over the floor. And for this to work, the air flows through the middle. There's a choke in the middle of the carburettor to lower the air pressure. Otherwise, the fuel won't be sucked out of the float bowl. The float bowl is kept at atmospheric pressure. So if you want this fuel to come out, you have to lower the pressure. So there's basically just a small drilling here. And what you can also see, if you're an engineer, is that the more fuel you've got here, you're going to have a greater fluid pressure head forcing fuel out. And that's really another reason you need this float valve, is that you have to keep this fuel over quite a narrow height limit in the float bowl to have any guarantee about how much of it is going to squirt out into the engine. So you can also imagine what might happen if you've got this in an aircraft and you try to engage in a sudden high-speed dive or climb. It's very obvious, really. All this fuel in here and this float bowl is just going to fly around all over the place. It's complete chaos and it doesn't work, and the engine cuts out. And so it's very unsuited to use in an aircraft. Now, that was a simplistic representation. This is a cross section through the actual Merlin carburettor that was on a Spitfire in the Battle of Britain. So there's two chokes, which you can see. They're just shown here as Venturis. The red stuff here is the fuel issuing out of the tubes from the float bowl in the carburettor. So the yellow piece is the float, and that's literally a lump of cork. The green bit is the little valve that stops the fuel coming into the float bowl. So the float bowl petrol is dark blue, and the fuel coming in from the low pressure pump is light blue. So basically, it's really just a tank of petrol held at a fairly sort of strict limit of height, and you've just got some tubes, some drillings issuing from that, which enable the fuel to come out in a fashion that you hope is reasonable. And when this is all on the ground on a static test bed with a lot of widgets added to it, it actually works reasonably well with a lot of refinement, because there are lots of different jets, there's an accelerator pump, there are all sorts of little compensation gadgets, and on a fixed test bench on the ground, it's actually just about a reasonable thing. But aircraft don't sit on the ground. It's actually where they spend the least useful portion of their lives, so it's not a good environment to judge the carburettor from. So to understand what happened to this, we're going to have to jump really a long way back in time, right back to 1914. And at that time, this wasn't called the Royal Aircraft Establishment. It was called the Royal Aircraft Factory, which was known colloquially just as the factory, because no one could be bothered saying Royal Aircraft every time. And so this was the premier source of aeronautical research in Britain in World War I. And it rapidly developed a reputation, good and bad, depending on who you asked. And in actual fact, it was supposed to be a research institute, but they did actually engage in designing their own engines and complete aircraft and actually manufacturing them. Not in great quantities, but they did actually manufacture. And this really upset a lot of the British aviation firms. And you can really understand why, because the Royal Aircraft Factory was designing their own engines and aircraft, and as a government-owned research institution, guess who was responsible for signing off new aircraft as airworthy? The Royal Aircraft Factory. So the firms basically said, look, you're self-certifying your designs. You just draw whatever you want, you know, sell it on, get it all made, and you self-certify it. And you can understand why they were not very happy about that, because they felt they got a raw deal. Because when they submitted their aircraft designs to the Royal Aircraft Factory, they got picked apart and drawn over the coals every time they did anything, whereas they said, well, Royal Aircraft Factory just turns out junk and self-certifies it. So in actual fact, the Royal Aircraft Factory and British industry started off in World War One with a very, very poor relationship to one another, and a lot of it wasn't even really very truthful, and it got very, very bad indeed. So Noel Pemberton Billing MP, who let's just say he's a bit of a character and leave it at that. Google will tell you more. He was heavily involved in British aerospace, and he really started off a company which eventually became Supermarine, not while it was under his guidance. And he was so angry with the Royal Aircraft Factory, he actually started off a parliamentary inquiry into the conduct of the Royal Aircraft Factory. And Mervyn O'Gorman at the time was the superintendent. And O'Gorman was basically fired after World War One, and the Royal Aircraft Factory was essentially neutered after World War One, based on the recommendations of this committee. And some of it's pretty amazing stuff. So I won't read through all of this for you, but these are the parliamentary minutes. And basically, Billing accused the factory of being full of communists and said they were all just sort of shirking work and getting paid for doing nothing and stealing things. And I don't know if it's true, but this is in the parliamentary meeting minutes. But one of the engineers basically spent a few months taking bits home in his pocket, and the police went round to his house and claimed to have found a complete aeroplane in his back garden, which he had built from bits stolen from the Royal Aircraft Factory. So this was alleged to be the kind of common thing that was happening at the Royal Aircraft Factory. So right at World War One, you've really got the position where industry and the centre of British aeronautical research have as bad a relationship as you can possibly imagine. And it was also full of lies, because the aircraft constructors, people like Sopwith, said that the Royal Aircraft Factory were no good because they just churned out junk. They were all scientists who didn't understand real manufacture, and the things were all just research projects. And that was probably true for the first couple of years of the war, but what they never tell you is that the Royal Aircraft Factory actually designed and built the SE-5A, which is widely regarded as the best aircraft that Britain flew in the whole of the First World War. And a large portion of that is that it's regarded as it's really one of the first planes that was ever designed from the perspective of being aerodynamically stable, because the Royal Aircraft Factory was the only research institute in Britain large enough to actually have real scientists looking at aircraft design. The firms were all very, very small, and they all had kind of mavericks working for them. They didn't have a big scientific staff, and the Royal Aircraft Factory did. So it's really not true to say they were just boffins who didn't design anything that was worthwhile. That's actually not the case at all. So after World War One, we were just thinking about what the next war was going to look like, and the only experience we had of being bombed were these lumbering Gotha bombers coming over from Germany, and they were unescorted. They're pretty slow, and once you've got the measure of them, they're pretty easy to take down. What's very interesting is that despite that, it's a real mistake to imagine that things like negative G were not being looked at in World War One. So this is from an Air Ministry file talking about the kind of manoeuvres that would be engaged in an aircraft in World War One, and it's just saying, fairly typical thing is to climb up above the enemy formation, dive down on it almost vertically, firing all the time, zoom straight up again. And he's also suggesting if you can dive steadily with the engine on full power, so much the better. So how on earth were we doing that in World War One and we couldn't do it in World War Two? Well, the one advantage of a World War One aircraft is that it's actually so simple that it can't go wrong. So a World War One carburettor isn't even a float carburettor. It's more or less just a hole for the air in the engine to go through with a pipe with a little precisely drilled hole in it, and fuel just comes out and we just hope for the best. And because it has no float bowl, it doesn't suffer from negative G cutouts. So we came out of World War One not knowing what that even was as an issue. Going into the 1930s, if you look at the Spitfire specifications, again, there's a lot of debate online. People say, well, we didn't care about maneuverability in the 1930s, so nobody minded that we had these hopeless carburettors because we just had to chase unescorted bombers, and it's not true. So if you look at the Spitfire requirements file, so this is mid-30s, the main requirements are speed, rate of climb, maneuverability, and ease of quantity production. You could argue that the last one didn't really turn out very well, but that's another story. Also, embarrassingly, going back to looking at the relationship between industry and the Royal Aircraft Factory, this was now called the Royal Aircraft Establishment by this stage, the RAE. They had actually started direct fuel injection research for aero engines in 1920, which would obviously have been completely immune to any engine cutting out problems. So I believe similar research was happening in Germany in about 1918, 1919. So I think you can assume that Britain and Germany were probably on a fairly even keel regarding fuel injection research up to sort of 1920. So in 1931, A.A. Griffith, who many of you will know, this is the Griffith who came up with the Griffith crack propagation theory. So he's the first scientist to ever seriously investigate crack propagation, as well as being a proponent of one of Whittle's denigrators, possibly, with the turbojet story. Very clever man. So in 1931, Griffith was working at the RAE, and he designed a fuel control system for a fuel pump that would be needed with fuel injection for an aero engine. So that's in 1931. So he just designed a control system. And this was developed quite soon into the concept of a pressure carburettor. So a pressure carburettor, to my mind, it's not really a carburettor at all. It's actually a very primitive single point fuel injector. So the reason I say that is that with a pressure carburettor, the low pressure of the air is no longer the thing which is sucking the fuel out. So the fuel is being put in above atmospheric pressure from a pump. So some pressure carburettors do have a choke, which you can see in the middle here, the restriction, but many don't. So the reason you can get away with having a high pressure fuel is that you balance the control valve. So the control valve has got the same fuel pressure acting on either side of it. That's C and D. The little valve in the middle meters the flow, and the air pressure, more or less atmospheric, and inside the delivery tube is acting on a little bellows there, which is A and B. And because C and D are pressure balanced, A and B can move the fuel flow valve with a tiny force without being influenced by the fact that the fuel pressure is much higher. So that's roughly how a pressure carburettor works. So it does away with the float bowl, and it's pretty good. It's very primitive fuel injection. So Germany, meanwhile, was leaping ahead, and BMW in the mid-30s were doing tests with fuel injection. And if you translate their reports from German, they report an increase of performance of 10 to 17% with the same fuel consumption. You can obviously also translate that into saying that you can also, with you're gaining a lot of fuel economy, of course. Meanwhile, at the same time at the RAE, unfortunately, not everything they did was perfect. And on 31st of March 1936, Dr. Morley wrote this pretty infamous report saying that the differences in power fuel economy with respect to different carburettor systems are barely measurable and of no significance, no practical significance. What's interesting is that this is in direct contradiction to all the studies that were being done by NACA in America at the time, and REE got all the NACA reports. So Dr. Morley was well aware that the Americans had produced results which disagreed with everything he had just said completely, which he makes no mention of. So in March 1937, he then tested fuel injection again and decided I'm not going to make any further tests. So Beatrice, meanwhile, had joined the Royal Aircraft establishment in 1936, sorry. And one of the first things she started working on were carburettors. And at the time, the manager of the RAE was A.H. Hall, and he has a bit of a reputation, if you read the history files, of being a bit of a what we'd call a night watchman. So his job really was to get the RAE through the years of austerity in the 1930s. And that meant not spending very much money, not doing anything very exciting, and just trying to scrape by with a few resources. And not a lot happened under his tenure. So in July 1941, Farron later succeeded him at the RAE and completely transformed it, obviously with the aid of a huge sum of money. And it was really only after Farron succeeded Hall at the RAE that things really started moving. And later on, Beatrice became in charge of engine accessories. That sounds a bit dull. Accessories meant magnetos and carburettors. It just meant not the core engine piece. Accessories doesn't mean brackets and things like that. So other things were going on as well. So even turbocharger testing was being done. And you can see here that this is just one of the RE notes talking about the RE carburettor testing plant in 1935. So this is really what Beatrice would have just about started working on. So Griffith was really a scientist, though. He's not an engineer, and it needed someone like Beatrice to come in and start turning his ideas, which were just schemes, into a real functioning carburettor. So this is what happened. So this is what Beatrice was working on from more or less the time she started at the RAE until late in World War II. So this is the RAE pressure carburettor, and it's similar to the diagram I showed you before. There's no float bowl, and in this design there's no choke, and you can obviously get straight away, so you're going to get more power with this because there's no choke. Now what you can do is you can say to yourself, well, why on earth do we care about a choke? If the diameter is too small, just make the carburettor an inch bigger so that the choke inside is the same size as the fuel pipe coming out and then the air pipe coming out, and then you can't have any problem. The trouble is that if you increase the size of the choke too much, basically what happens is that as the aircraft goes across its range of operation and altitude, the relationship between the pressure in the choke and the flow through the engine pipe are such that if you just make the thing too big, you get incredibly poor response between the engine air requirement and the fuel being drawn out. So the engine acceleration becomes progressively worse. So you can't just make it all really big. So that's why it's a problem. You can't just fit a huge choke to say it's not smaller than the engine pipe anymore. It has to be smaller, or your engine response will be very, very poor. So the yellow part are the two bellows, which you can remember from the diagram I showed you before, and the green is just the fuel flow. So there's no float in here, so it's completely immune to negative G. And that's another drawing of it here. So this is the RE pressure carburettor that Beatrice is one of the key people designing. So I think in the mid-30s, the number of staff was very, very low, and I would say it's probable that Beatrice and no more than about 6 other people were designing this, and it would have been a very, very small team indeed. So by October 1937, they had got to making an improved version of the RE carburettor. So it was Clothier and, as you see here, Miss Beatrice Shilling, and so it was getting quite close to being an operational item here. What's interesting here is that at the time, or just afterwards, the RAE wrote to Rolls Royce. So this is a letter here. You can see at the top, LOV. So that's Cyril Lovesey, very senior engineer at Rolls Royce. And what he's written at the bottom here, comparing Beatrice's carburettor with the conventional types, which would be the float bowl. He says practical results show there's practically nothing to gain with the RE carburettor. So they're looking at fuel consumption and other things like maximum power. These are tests on a fairy battle of all things. And this is just another page of the letter. So he says the idea with this is, because this talk's going to be recorded, I recommend you just look at the pieces of text which are highlighted, and when it's released online you can come back and read the whole letter in your own time. So just look at the highlighted text, please. So this is Cyril Lovesey writing to Ernest Hives in charge of Rolls Royce. So the practical advantages offered by the RE carburettor may not be quite as marked at the present time. We've had very good results with our Merlin SU carburettor, which is simple and gives very consistent results, which is more or less nonsense. It gives consistent results on the ground only, or if you fly straight and level. What's also interesting is that Rolls-Royce used to make their own carburettors, but discontinued it in order to work on more general engine problems, which is that's an interesting comment. So I think that would have been in about 1930. So another way of interpreting that would be that carburettors started to get a little bit too difficult for them. That's how I would interpret that comment. So let's look at what happened when the RAE did tests of the Merlin SU carburettor. This is June 1939. Now, bear in mind, this is very shortly after Cyril Lovesey's letter that you just read at Rolls-Royce, talking about how consistent the Merlin float carburettor is, and it's not. It's hopeless. It should never have been on an aircraft. It's so if you look at the top graph, that's angle of tilt. So and that's the percent of ideal fuel flow that you want as angle of tilt. So you get the amount of fuel flow you want is 0, and basically once even an angle of tilt, moderate angle of tilt, you're going to get sort of 15% less fuel than you want. And if you have an angle of tilt anything more than 30 degrees, it basically stops working. And the same is true in climbing. If you get to an extreme angle, that's less of a problem in climbing because you'll probably still anyway. What's also interesting is that the same thing happens just when you bank the aircraft. If you turn left and right, it's not just diving. So the fuel flow, which I've highlighted in yellow, completely changes depending on the bank angle. So it's not a consistent machine at all. So what Lovesey was saying is just untrue. And this started to come out very slowly in practical tests. So 19th of October 1938, Martlesham Heath tests of a Spitfire. Unsatisfactory features are engine cutting out at high speeds, and in a dive it doesn't run correctly. So this is where it started to come out. There's a test of the Hurricane. This is an interesting one. At full throttle dive, the engine gave a slight cough as the dive was entered, and they said this is momentary only, and it's not considered to be important because the trim between engine on and off was small. Now, what the trim means is that basically the attitude of the aircraft didn't change that much. So this is a test pilot reporting. So you can imagine that maybe he thought at the time he hadn't considered what the implications of this would be if you were flying against someone who wasn't flying a plane with this problem. But nevertheless, it was clearly known before the Battle of Britain that this was not entirely satisfactory. So Beatrice Shilling was approached at the RAE. So this report, it doesn't have her name on it, but if you read her biography, progress statement number 4 is listed as being written by her, and I think that must certainly have been the case. So what's interesting, but this is Beatrice's report on why the Merlin engine was cutting out in the Battle of Britain, 24th of June 1940. What's fascinating is that the float bulge thing that we all talk about was just one of many, many points, and she basically just completely destroyed the float carburettor and just said it's fundamentally hopeless. There are actually there's the physics doesn't work. It's not just a question of improving the design. So there are all sorts of things about it which just don't work. The altitude needle doesn't work. The float chamber fuel level isn't consistent. The delivery tube doesn't work. There's frothing in the carburettor float chamber. There's unvaporized fuel particles. It goes on and on and on. So Beatrice Shilling was now really asked to come up with something to fix this, and this is what the restrictor was. So meanwhile, the RAE carburettor, which was completely immune to the whole problem in the first place, was being fitted to Hercules engines for trials. What's interesting is that most of these trials really ended up being supported by the Hobson company, and the way British industry was set up is that the Hobson company carburettors supplied Bristol and a couple of other more minor makers, and the SU company, who made the Merlin carburettor, supplied Rolls Royce. So that's an interesting difficulty as well. So by this point, they've also highlighted in the report that Beatrice's carburettor here uses a similar method of fuel control than the German direct fuel injection systems also use. That's the one Griffith laid out in 1931. Also, what we have to also talk about with the restrictor that Beatrice designed is that this was a much bigger problem than just sitting in a meeting room and Beatrice saying, I've got an idea. It was such a serious problem. You can see here Farron wrote about it after the war. It says they formed a very large team drawing from all useful points throughout the entire Royal Aircraft establishment. So this doesn't mean that Beatrice didn't come up with the solution. It means it was such a severe problem they had to get a huge number of experimental staff to try and work out what was even happening. So probably what happened here is that many very complex tests were done, and Beatrice was one of the people looking at all this, and she came up with this simple idea. So the fact that a large number of people were involved doesn't mean that you get this restrictor that she designed and divide it up into 100 slices and say that she designed one slice of it. That's not what I mean at all. It's just to show you what a huge problem it was, and this was not a one-person problem to fix. Farron writing here was writing this in 1946, so he was one of the very important people in Britain, and he was interviewed and asked to give his sort of opinion in hindsight with everything that had gone well and poorly in the war. So this is Farron writing, and you can see he said that the engine companies bought their carburettors from small, poor, badly organised industry. When RAE produced their carburettor, which was what Beatrice Shilling had done from Griffith's initial scheme in 1931 in the middle of the 1930s, the firms didn't appreciate it and were reluctant to believe that the magic had been taken out of carburettor design, because the companies like SU didn't have their own big scientific and experimental staff. It was really done by a lot of trial and error and judgment, and yeah, that's how they felt about it. And he says, we did make a great effort to sell Beatrice's RE carburettor to the firms, but at the time this effort was being made, even the RE didn't appreciate all the advantages. So he's not blaming just the firms, he's saying they also did a bad job selling it, particularly its immunity from the effects of negative G. So that was one problem. Even the RE didn't know the full benefit of what they had. So when the negative G was found out to have caused the engines to cut, RE devoted all their problems to finding a cure. Although, and this is Farron's words, if their own carburettor had been in service, this would never have been necessary. So that's straight from the horse's mouth. So Beatrice should never have needed to even design the restrictor. She'd already designed with Griffith and Clothier and Swan at the REE a much better carburettor than Rolls Royce could ever come up with. Now this is going to be very interesting, especially when we get to the end of the presentation. So I don't have his photograph, but this is another RE engineer saying just how much of a panic this caused in the Battle of Britain when the engines started cutting out with the Merlin float carburettor, and they really got into a panic. Also hearing about it from headquarters, which is very interesting. What's really interesting is that this was a problem with two facets to it. It wasn't just that the RE and Beatrice had already designed a much better carburettor. It's that Rolls-Royce devoted a huge amount of their own time. They went and designed their own carburettor. So this is after the Battle of Britain. So Beatrice was designing the restrictor to solve the problem of the float carburettor because her carburettor had been ignored. Rolls-Royce said, we're going to go and design our own carburettor to fix it. So that's a diaphragm carburettor, and it didn't work, and it was cancelled. So Rolls-Royce devoted a lot of engineering effort to that, and it never worked. And that included, that was being developed by Cyril Lovesey headed that. And so Lovesey was one of the most senior engineers at Rolls-Royce. So imagine the time wasted during the war on that. This really started to come undone a little bit when we started to do tests of the German fuel-injected engines that we'd captured, and reports started coming back of Beatrice's carburettor from the Hercules tests saying the tests are entirely satisfactory and we're now going to test it out with the Merlin. But again, this was too late to be of use. So Rolls-Royce really only got as embarrassed as they deserved to be when we first captured a German fuel-injected engine, which of course didn't suffer from any of these problems. So this is the first aircraft shot down in Britain. It's a Heinkel, shot down in the Lammermuir Hills near Edinburgh. So a few Rolls-Royce guys were sent up, and they got it. And they basically hacksaw the engine out. And I'm getting a bit of echo from the audio here. I don't know if we can do anything about that.
I've just muted the participants again.
And that engine was taken down to Rolls-Royce and tested within a few days. And Rolls-Royce were forced to admit that it was actually really jolly good. So the direct injection system, it's pretty complicated. So, but conceptually, it's actually not that complicated. If you just look at the diagram on the left, there's a little plunger which goes up and down on a cam, and there's a little air pressure capsule on the right, which just turns the cam, which has got a little spiral groove. And depending on the angle of that, it allows the fuel to come out earlier to adjust the amount of fuel from a fixed plunger stroke. So it is quite complicated. The Germans had actually started off with a carburettor, which is mounted between the V inverted there on the left. That's a Daimler-Benz engine with a carburettor, and on the right with the direct injection system. And you can see the fuel economy improved from 240 to 205 grams per PS per hour. So it was a major improvement, which we at the RE had also been developing since 1920 and had been ignored, just like Beatrice's carburettor. So this is the Rolls Royce diaphragm carburettor. So this is a brand new carburettor they developed with SU to try and solve the negative G problem, and this was cancelled. It didn't work. So what they had done is the pink piece is the little lever that opens the fuel relief valve. The green is atmospheric pressure, and basically the pink lever was weight balanced. So if you joggle the unit up and down, the float arm angle doesn't change because it's weight balanced. And there are also little ball valves which jump up to stop the fuel shooting out of the float bowl, and it just didn't work. And even in the manual, it sounds a bit dubious. They say the fuel supply into the diaphragm chamber and the diffuser is regulated for a reasonable period. So even according to their own spec, it was really just quite a poor solution, and it was cancelled. It was tested very briefly with the Merlin 50 in one squadron, and it failed. So one of the people who collaborated with Beatrice on the pressure carburettor was Captain Swan, who was head of the engine department at the RAE, and he was interviewed in 1946, and here's some comments from him on the whole story. And basically they discussed the carburettor, and the whole thing was given a priority B in the 1930s. And he seems like to have been a fairly typical engineer, which is that he basically said that because he had been working on this, he didn't feel it was really his job to sort of press it forwards. Now, when it says here his own invention, we need to be fair here. Swan actually started working on this before Beatrice joined. So I don't think he's trying to cut Beatrice out there by saying that. Although I have to say that in Swan's interview, he doesn't mention Beatrice. So we can also say that that's maybe not as grateful as it could be. So we can see it wasn't a thing where there just wasn't enough time to develop it. Several years passed between when the carburettor could have been manufactured and when it got a contract. So Swan blamed headquarters, that means the Royal Air Force, the Air Ministry, and they could have made a bigger effort with the firms. But Beatrice did get the last laugh, because Hobson's did take up the contract to manufacture en masse the RE pressure carburettor, and it was successful and made in very large quantities, supplied lots of different engines. So we did get there in the end, but it's an embarrassing story for Britain. It really is. So these are just some more discussion points. So it's not just the carburettor. So we need to press this point home. I don't think this is an isolated thing where you can just say Beatrice was ignored because she was a woman and everything else went well. I think this goes back to a serious problem with managing aviation research and science, although I'm sure Beatrice had many difficulties with the culture as it was back then as well. But I don't think that was responsible for the carburettor being ignored. So even variable pitch propellers and automatic pilots were ignored, and people were saying it's this same lack of interest which relegated the RE carburettor to what they've called cold storage. So a lot of people actually blamed the Air Ministry as well, and you can see, though, being sympathetic to them, it's very difficult for them to solve, because Air Ministry staff are administrators really, and as you can see here, the RE carburettor, which Beatrice had worked on for so many years, was quite a radically new invention, and the people at these desk jobs, unless you're reading all the current scientific papers, you're just not going to understand what's in front of you. So you can appreciate how something like that can end up on someone's desk at an Air Ministry and just get ignored. It might look unbelievable to a technical person, but a lot of these people just weren't qualified to understand what they were looking at. It does go back to the relationship between the RE and the firms. Again, this is a post-war review saying that larger firms who didn't need the REE tended to ignore them. And that independence was proportional to success. So if the firm was doing well, they didn't bother consulting the REE at all. And this is quite damning. So this is Sir John Buchanan, who became technical director at Short Brothers, and he basically said, so long as the firms, by which he means Rolls Royce and so on, were in a restricted market, the feeling existed that firms using REE devices were using them because they couldn't think of anything themselves. So I think that really does hit the nail on the head. I think Beatrice's carburettor was ignored because they were so embarrassed that they couldn't come up with anything themselves. They felt like going to the REE was like going back with cap in hand, like Oliver Twist, and asking for some more soup. I think they were just so ashamed they couldn't face going to the REE and saying, we don't know what to do, help us. I think they just couldn't face it. I think it was just complete embarrassment. So just running through a little post-mortem, we've got World War One. The Royal Aircraft Factory is sidelined by industry through jealousy. The REE is the centre of fuel injection and pressure injection carburettor research in the 30s. Rolls Royce gives up developing their own carburettors. SU and Hobson are left as the sole suppliers. SU only supplies Rolls Royce and Napier, and Hobson supply Bristol and Napier. The huge expansion in industry in Britain in the 30s sort of bypassed the REE. They didn't really get a huge funding boost because they were seen as a research institute, whereas the money was going to building shadow factories for mass production of Bristol Hercules and Rolls-Royce engines. The REE also lost a lot of its best staff because they had such a low budget that a lot of their best people just left, and the conditions there were absolutely appalling by all accounts. So when Shilling was working at the RE on the pressure carburettor, taking Griffith's scheme for the controls and Swan's initial idea, they were all working under severe financial austerity. And finally, Rolls-Royce is offered the RE carburettor and says no. Now I'm really going to come right back to the start again, because this really is the smoking gun that you always hope you're going to find. The reality is that the Air Ministry, they knew all along. So this is a survey that was done at RAF Hawkinge in Kent on the 13th of November 1932. It was organised by the Air Ministry headquarters, and it was basically a survey to look at the design of the next home defence fighter. So they basically consulted all the pilots at Hawkinge to get their feedback on what they wanted from their aircraft. And one of the key points that was sent back to RAF headquarters is that the pilots said they want inverted engines, chemically cooled. That means using ethylene glycol for the coolant. They tended to call it that, with an improved carburettor to stop cutting out in sudden dives. So they knew since 1932 that pilots in the RAF were really upset about having engines that cut out with negative G. So at some point, this report would have been put on somebody's desk in the Air Ministry, and they would have basically ignored this. So I don't think it's a conspiracy. I think it's probably, going back to the earlier letter we saw, this probably ended up on the desk of someone who wasn't an engineer or a scientist, didn't really understand technology, didn't understand what they were looking at, and were not qualified to interpret it properly. But you can't say they didn't know. However, as I said, Beatrice did get the last laugh. Her pressure carburettor was put into production, so all Napier Sabres from the 4 onwards had it. So the Tempest fighter flew with Beatrice's carburettor, and the conclusions were It's very satisfactory. The movement of the pilot's throttle is quicker than with a float carburettor. Acceleration is extremely smooth, and the injector is not affected by aerobatics or the sudden application of positive or negative G. So she did get the recognition she deserved in the end. So it was also fitted to the Bristol Hercules and the Bristol Centaurus engine. So she did get there in the end, just many years after she should have done. So I hope you've enjoyed that. This is the point where I'll try to help you with any questions.
In your book, you discuss the value of the Schneider Trophy in accelerating aero engine development in the US, Italy, and Britain. Is it possible that the defects of the conventional carburettor were less evident in low-altitude speed contests, directing British focus away from some of the benefits of fuel injection?
Yeah, I think that's a really good point, and I think that's entirely probable. I think that's a. I think I don't have a letter saying it was or it wasn't, but I would think that that was definitely a contribution to the lack of exposure to the problem, which, as I've shown, was given on paper to the Air Ministry in 1932. So yes, basically, I think your point is correct.
Good. Just a comment from my side. So this pressure carburettor, it's a very elegant design. I wasn't aware of it. A very elegant design to dispense with the float chamber and all the problems associated with that altitude. And you also mentioned about the Venturi size, that you can't just scale up a carburettor and the Venturi size to, and for the sort of operating envelope that you're talking about in terms of altitude and sort of engine performance. But when I think of SU carburettors, I think of the sort of thing you used to have on your Mini and stuff like that.
Yeah.
And they were like variable Venturi. And I just wondered if there was any, was this because we're talking about fuel injection and fixed choke carburettors? Was there any discussion, or did you find anything about variable Venturi carburettors, or was that not a thing?
I haven't seen anything.
No.
So I'm sorry, that's a really short answer.
No, that's okay. It is what it is.
Yeah.
Okay, we've got another one in the chat. Is there any evidence in relation to accidents, fatalities caused by these failings?
I can only answer that peripherally. So my research tends to be more on the technical and later now on the organizational side. My operational research is of quite a poor standard, so I don't pore over squadron reports and things like that. But what I will say is that it must definitely have caused, in addition to the problems in combat, a lot of accidents, because there's a letter I'll need to go and check who wrote it. There's a letter. Someone was sent off to, I think it's F.R. Banks, actually. I think he went to America. And this is in the very early 30s. And he came back and wrote that the Americans were making strides ahead in getting rid of float carburettors. They couldn't stand the things, and he said that this whole problem was very, very well known in American civil airline pilots, because he said that a lot of the runways in America were so bumpy that it was a fairly common thing to lose an engine on takeoff, purely because of the bounce on the runway causing the float variation to cut out. He said that there's many civil pilots who've lost an engine literally when they're just about to leave the ground. So you can imagine, if you're in a 2-engine plane, I mean, you're probably going to crash at that point. So I would think in civil aviation, it must have caused countless accidents, and that's before we even get into icing. That's just the float bowl.
Okay, yeah. Next question. Is there anything reaction from the Americans after putting the Merlin into the P-51, or did that use a different carburettor?
As soon as Packard started making the Merlin, that they had their own carburettors. on that,
Okay.
which were Bendix carburetors. So all the Packard Merlins that were used, because a lot of Packard Merlins were used on British planes, loads of them went into Lancasters and stuff like this.
Mhm.
They weren't just used in Mustangs. So they essentially all had American Bendix carburetors. So that wasn't just because they thought float carburetors were useless, which they are on an aeroplane. It's also because they didn't want the logistics of us sending crates of carburetors over to America and then them sending the engine all the way back again. They said it's got, we have to do it all here and then send you the finished thing. So yeah, they Packard's Merlins didn't have float carburetors.
Okay. Next question we have is, can you tell us a bit about Beatrice as a person? Did you find that in your research? Anything specifically about her character?
I'm embarrassed to say I don't have enough information to kind of give you a really good gauge on that. But I have found, I've only found a few snippets which I think might be instructive. What I would say is that if you're interested in that, it's out of print, but you can get it secondhand. There's a biography. It's quite short of Beatrice. I think it's called Negative G, actually, or Negative Gravity. I think it's called. You can get that on. If you go onto Abe Books, ABE Books, it's great for used books. I'm not going to repeat anything from that because I didn't write that book, and I'm simply repeating what someone else has written. But I did see a letter that I had actually copied, which talked about Beatrice a little bit. So Beatrice was one of a very small number of engineers from the RAE who were sent to Germany to interrogate German engineers after the end of World War II. So there were about 15 sent over in total, of which Beatrice was one. And I have seen letters that hinted that Beatrice was very severe in these interviews. I don't mean that she took in a stick and started beating people up with the stick.
No, she's a tough cookie.
I mean that I think she was very, very rigorous and probably didn't have a lot of patience and probably didn't have any time for waffle. And I think she went in and started talking to someone and just wanted to get on with it. And if they were trying to play for time or sidestep the issue or hide things, I don't think she had any patience for that at all. So that's how I would read between the lines. So I think she was probably pretty hard-nosed, and I think she would have been quite a strict boss.
I can imagine.
Yeah.
So another question, how much capability, not just relating to the carburettor, did we miss out on with the Spitfire versus other offerings? I guess that's a very big question, but maybe if you've got some initial thoughts to share.
It's hard to quantify that because you can take kind of alternative history too far because you have to be realistic and understand the constraints at the time, and that I think that's why it's so important to understand things like going right back to World War One to understand why people didn't like using RAE stuff. It's not, they didn't wake up one morning and just sort of say, I'm going to decide not to like these people. There's historical reasons for everything. I think that probably what should have happened is that I think if we'd have put a huge amount of effort in, which is not to say more effort than we had available, I just mean focused effort, I think Beatrice's carburettor could have been in a Spitfire in 1939, and that would have saved the lives of quite a few British pilots. Because remember, you might just think it's the German pilot getting away, but that means they come back the next day.
Yeah, so of course. Yeah.
It's not just saying the engine cutout is going to make my aircraft explode. It's lots of RAF pilots would have died because of that. So I do think that the also, Rolls Royce wasted probably 6 months designing their own carburettor in the middle of a war that didn't work, trying to solve it. They could have spent that time improving the Merlin. And I think also it's important to keep in mind that if you bring up carburettors and all this kind of thing, it's people always talk about the advantages and so on, but I think if you combine the time Rolls-Royce wasted designing their own one, if you look at the engineering effort that went in afterwards, I think it would have been an economy to focus on Beatrice's stuff in the late 30s. I think it would have saved us a lot of time in the war, because you don't want to be doing this stuff in the war. That's not a good time to do development work, because you're getting bombed and this kind of thing. So it's a bit, I don't think we've got time on the call to get into sort of missed avenues with the Spitfire, but that's a big one. There are many of them. I don't think they're the purview of Beatrice, really.
Okay. Another question is that obviously from the slide, the first slide you showed, so you obviously had a background and interest in motorcycle racing. Did you find anything out about that? About whether she achieved anything in specifically in motorcycle racing, or was she just an enthusiast?
I just haven't researched that. I have to be really picky about what I research.
Yeah, of course you do.
Yeah. So I think it's a horrible answer to give. I have Googled it in the past. There is a reasonable amount of information on that online.
Okay.
And there may well be stuff in archives which tells us more about that, but I don't have it, I'm afraid.
Okay. Good. So one of our colleagues has just mentioned in the chat window that he's found a book on Amazon about Beatrice called The Girl Who Could Fix Anything. So that's a general bit of information.
Yeah, I didn't know about that book. It's probably, I think it must be quite a new one.
Okay. And another question here. Did the UK develop automatic mixture control like the BMW 801 Commando Gerhardt?
Yes, Beatrice did.
Okay.
So that was later combined with the pressure carburettor, and it was used on the Centaurus post-war, and that was known as if I get this right, the Hobson Master Control Injection Unit. So that basically had a complete control system inside. So that was a combination of the pressure carburettor and the engine controls, Hobson Master Injection Control Unit. I'm not saying it was all exactly the same as a BMW 801, but it basically did the same thing as that, the Commando Gerhardt. So yeah, we did do that, and it was Beatrice.
Okay, interesting.
It's called Hobson, but that's just because Hobson bought the manufacturing license from the RAE. That didn't mean that Hobson then went and did everything on that afterwards on their own. Beatrice was involved with that whole thing. Hobson just had the commercial rights.
Okay. It was interesting for me when you showed the picture of the fuel injection system, because the sort of the core of it looked like a diesel inline fuel injection pump, the way that it, this sort of the design of it. So that was quite interesting for me.
They're almost exactly the same, and it's interesting that you'll get people saying that injection was too complicated, because any agricultural engine manufacturing factory in the world was already making those pumps. The only difference between a tractor fuel pump and the fuel pump on a Daimler-Benz 601 is that because petrol doesn't have self-lubricating properties like diesel, they just had to introduce some little tiny oil channels to lubricate the plungers. So the pump it's got quite high oil consumption. But aside from that, it is essentially indistinguishable from a tractor diesel fuel pump, and that's what it was all developed from. So yeah,
very interesting. But you also mentioned obviously an improvement in fuel consumption. a decrease in fuel consumption because of the direct injection. And you also mentioned that BMW stated a 10 to 17% improvement because of fuel injection. Did you find anything that specifically sort of mentions what the benefit was of fuel injection over these carburettor designs? Is it just it's balancing of the cylinders or something, or was it something more subtle?
Most of it's down to cylinder balancing.
Okay.
Because when you're right up on the detonation limit, you can't afford to run too lean at all. So the whole fuel supply has to be tuned. So the engine with the cylinder with the worst air supply gets enough. The cylinder with the which ends up getting the most air doesn't run lean. So that means half the other cylinders are running far too rich. Okay.
So good. Okay, I don't see any more questions popping up in the chat window, and I don't have any more questions. So thank you, Calum, for dealing with all those questions and giving such good succinct answers. So very interesting in the presentation.
I'd just like to make the one final closing point I'd like to make is that if I'm 100% convinced if the RAE had been given the funding to do direct injection systems, I'm sure Beatrice would have been at the centre of that development as well. It's when she joined the sort of magic fuel project was the pressure carburettor. But I think if we'd have focused on injection, I'm sure she would have been doing all that stuff as well.
I can imagine. Easy to be wise after the event, but yeah. Anyway, I would say we need to give you a break now and perhaps say thank you for the excellent talk. So we've already got some feedback here in the chat window. Everybody's enjoyed the talk, and I really appreciate the fact that you premiered this for us in our little IMechE Switzerland group. So we're very grateful for that. And thanks to everybody for joining. And we hope that you enjoyed it. Please take a look at the IMechE Near You website, where you can see what's going on not only in Switzerland but also in Europe and other areas. So please check out the events and the IMechE events and join them and support us in putting the program on. So I guess we can do a wrap up, and I would say again, Calum, thank you very, very much for this, and we really appreciate it, and the audience did too. And I guess we can close the event. Say thanks again to everybody. Thanks for joining. Hopefully we can see you again in another event, either virtually or physically. And I guess thanks to all, and I wish you a nice evening, and we can close the meeting and the presentation.
Thanks very much, David.
Thanks a lot, Calum. Thanks again, and thanks to everyone for joining, and hopefully we'll see you again in the future. Thank you very much.
Thanks
Cheers.
for logging in. Goodbye.
Goodbye.